All right, we're going to see how much we can get knocked out here in 10 minutes. I'm hoping for 5. Let's see what happens. So to start us off, we're going to look at this first problem that has a linear approximation. Okay, so for linear approximation, it's the same as tangent line approximation. We're going to give us a visual here. We're going to graph this function f of x. Our tangent line is going to be at the a. It's going to be at 9. And we're going to be plugging in 8.2 to get our estimate. So what exactly are we doing here? Well, we need a tangent line. So let me first graph f. This is generally what f looks like. And then we have a equals 9, which gives us a value of 3 right on the line. And what we're going to do is we're going to make a tangent line so that we can then plug in 8.2 into the tangent line to get an estimate. 8.2 is right here. Of course, we could just plug in 8.2 into a calculator, but then we wouldn't be getting an estimate. We would be getting an exact number. So here's our tangent line. Instead of plugging in 8.2 into the function, we're going to plug 8.2 into the tangent line equation, which won't give us the exact value, but it'll give us a value that's really, really close to the line. So you see how that answer would be really close to the actual answer. Looks like it would be an overestimate right here. Now, it's important to note that 8.2 is pretty close to 9. It's the distance right here isn't that big. The distance between 8.2 and 9 would be called delta x, because that's a change in x. If we had an x that was farther away, like right over here, I don't know, maybe 4.1, then what we would get is we would get a number that's really far away from the actual line, and that wouldn't be a good estimation. So we want to make sure that our delta x is not that big. It needs to be small so we can have an accurate estimation. Let's go ahead and find our tangent line equation. So we're going to need f prime of x, which equals, let's see, I put x to the 1/2 power instead of the square root of x, so I can drop the 1/2 down in front and then take 1 away from the 1/2, which gives me negative 1/2. This can be written as 1/2 times x to the positive 1/2, so I drop the x down to the bottom of the fraction so that we have a positive exponent. And then we have our trusty old, what's this called, tangent line equation. All right, so we got to plug 9 into all these a's, and since my a's kind of look like 9s already, I'm just going to extend their legs out. And then we get y equals 3, or y minus 3 equals f prime of 9, so I got to plug 9 into this, which would be 3. The square root of 9 is 3 times 2, which is 6, so we have 1/6. And then if I plug 9 into there, we have x minus 9. So there's my tangent line equation. And like I said earlier, we're not plugging 8.2 back into the f. We're plugging 8.2 into our tangent line equation to get an estimate. So let's go ahead and do that. So if I plug that in, I'm going to move first the 3 over. If I plug it in right here, I would get negative 0.8 with a 1/6 multiplying to it. Then I got to add 3 to it. Let's see, that would be the same as 8/10, negative 8/10. If I simplify that, that would be 4/5. Then I have to add 3 to that. Now the 6 and the 4 are going to cross cancel out by dividing each of those by 3. So I get a 2/5 and then a 1/3, and then I multiply straight across to see what I get. I get negative 2/15 plus the 3, and then I get, when I add those together, see, that would be a 2, no, not 3, 2. We have 2 and 13/15, and it looks like none of my answers are fractions, which kind of stinks for me. Looks like maybe this is a calculator problem, I don't know. So I want to take that 13 divided by 15 to get my decimal. I have 130 divided by 15. Let's see here. Let's try 8 first. 8 times 15. It looks like we only have 8 and 7 as our choices. So if I multiply 15 by 8, I get 120. That's perfect. So I go 120 and I subtract. I get 10. And then I add a 0, bring it down. I got 100. 15 goes into 106 times. And so I do this again. Let's see, I get 100 again. So I get 0.866. So then instead of that fraction, we got 0.866. So it's 2.866. So Where'd my answer go? Oh yeah, up here. So there's your answer. It is letter B. All right, next one. All right, this problem is kind of neat. It already gives us f prime. So this is f prime. Where does f have a local minimum? Where is it? Okay, so that means we just have to find the x. We don't have to actually find the local minimum. And just as a recap for you all, if I just have a curve right here, your local minimum is going to be where the slope equals 0. So that's where f prime equals 0. It also gives you local maxes too. It's also important to note that if we have something that looks like this, or even something that looks like this, that cusp right there, that can also give us a local minimum, but that would be, the slope right there would be undefined. So let's see what we got here. So we got our slope here, our slope function. It's going to be x to the second power minus 9. I'm going to change it to the 1/3 power instead of saying the cubed root. We're going to set this dude equal to 0 to find out where our local minimums can be. Let's see, if I cube both sides, I'm just going to get x squared minus 9. And then if I wanted to solve this, I can move that 9 over. I don't have to factor it. I can move the 9 over, and then I get x equals plus or minus 3, which would be great. But I see a minus 3 and a plus 3, so I'm not sure which of these is the answer. And then the other thing I need to consider is, can I plug something in here that would make f prime undefined? And I don't think so. There's nothing I could plug in here that would make f prime undefined, mostly because this is a third root, and you're allowed to have negatives inside of a third root. If this was an even root, like a second root, like a square root, or a fourth root, then we could probably find an x that would make this undefined. But doesn't look like we can. So -3 and 3 looks like our only possible choices. And so to help me find out which one's a minimum, I'm going to do a sine line graph for first derivative test. Now let me explain to you why. If we're increasing, meaning the slope is positive, and then we start decreasing, then this is going to be a max. And I don't know if this is at 3 or -3. If we're decreasing then increasing, then we have a local minimum, which is what we want. So we're looking for a decreasing then increasing scenario. So we get -3 here and 3 here. I got to pick tester points. So I'm going to pick -4, 0, and +4. Now let's plug stuff in. Now we're going to plug this in, because it's the first derivative test, back into this guy. If I plug 0 into this guy, that would be -9, the third root of -9. And I don't need to find the third root of -9. I just need to know that that would give me a negative number. Because if I was raising something to the third power, that would be 3 times. And in order to get a -9, all these numbers would have to be negative. So it looks like, I mean, this could be negative plus right here, or we can have a plus then a negative. It looks like 3 is going to be our answer. So I'm going to double check. Since I can't have 2 answers, I'm going to go ahead and just plug in the 4 to see if I get a plus right here. Because if I get a plus right here, that means I found my local minimum. So let's plug 4 in. So we have 4 squared, which would be 16. 16 minus 9 would be 7. The third root of a positive 7 would be a positive number. So it looks like we found our answer. Our answer is going to be, no, +3. All right, pictures are my favorite. Oops. The graph of f prime is given at the bottom left. Well, that's what it says in your book. Right here, it's right above it. Thus, f has a local minimum at... All right, now I always like to do this. It's kind of silly to some, but I like to make sure I know that this is f prime. Or sometimes I just go like this. I point an arrow. This is f prime. We need to know that this is f prime, because I don't want you guys to say that the local minimum is right here and right here. That is definitely nah. That's not true. We find our local minimums wherever f prime is equal to 0. So we're gonna find it right here. We're gonna find it right here, or we're gonna find it right here. Those are the only places where it can be. Now, some of you guys would go ahead and maybe you would graph f by looking at this graph and to figure this out. That would probably take too long, but it is effective. You can find the answer to this by doing that. Instead, I'm going to just draw a sine line graph, because I'm used to reading that, and I can easily describe this to you guys by using a sine line graph. So if I have -1, and I still probably wouldn't do this by myself, I can see the answer really quick. All right, so before -3, it's positive. Between -3 and 1, f prime is negative. And then what about between -1 and 2? Looks like f prime is positive. And what I'm looking for is just that f prime is it above or below the x-axis. And here, after the 2, we're also above the x-axis, so that means f prime is positive. All right, guys, do you see it? Do you see where the local minimum would be? Right here, we're increasing, then decreasing. Increasing and decreasing gives us a maximum. Decreasing, then increasing. Decreasing and increasing does give us a minimum, so it looks like we're at -1. That's our answer. And since we already did this, let's go ahead and answer this next question. Using this graph, f has a local maximum at x equals, we already figured it out, -3. So -3 is your answer for number 4.